Okay, hello. This is the test 4 version 1 solutions. So, question 1 here. Literally an infinite number of ways you could have solved it. I did make a slight adjustment here on my version that I didn't even think of until someone asked me during the test, and that was that someone asked if they could make one of the two waves just perfectly horizontal here with an amplitude of 0, and that would be the trivial solution. So I said no, and someone else wrote that they could have done it on the test, but they did not do it. So I added a little disclaimer here that the requires the waves to have a non-zero amplitude. But anyway, so here we are given a wave that it just looks like a regular sine or cosine wave, and we are asked to draw on the larger graph two different waves with a non-zero amplitude that could have created the wave given to us. So I will note that this peaks at -2 and +2, so it has an amplitude of 2. So I'm going to draw a wave that most people drew, one that goes to -3 and to +3. And there we go. And then they also drew a wave that goes to +1 and -1. Excuse me. So most people drew these waves here, and that was absolutely correct. So the amplitudes are right here. We have an amplitude of +1, and here we have an amplitude of -3. Together, they give us an amplitude of -2. And then by the same logic, we get an overall amplitude of +2 over here, which is what we have here for this wave. And we have zeros in all the same locations. So not terribly complicated. Moving on to number 2 here. A specific frequency is very often observed in astronomy as a strong indicator of hydrogen. This corresponds to a very well-known wavelength of light known as the 21 centimeter, or 21.1, if you want to be more specific, centimeter hydrogen line. So that is the wavelength, and you are asked to calculate the frequency of this light. So we know the speed of light is c, and we know that the speed of a wave, given by the wave equation, is equal to the frequency times the wavelength. We are asked for the frequency, we know what the speed of light is, and we are given the wavelength, so we have everything we need here. Rearranging for frequency gives us c over lambda. C is 3 times 10 to the positive 8 meters per second. Lambda was our 21.1 centimeters, so I'm going to multiply by 10 to the -2 for centimeters. And that gives us a frequency of about 1.42 gigahertz. That is times 10 to the positive 9. So I also accepted 1.42 times 10 to the 9 hertz. And some people just wrote out the full number as well. That was also totally fine. But that was the answer there. 1.42 gigahertz is what I was looking for. Number 3, a mass on a spring oscillates and completes 300 cycles in 10 seconds. Find the frequency of the system. So for frequency, that is the number of cycles over the change in time. So that gives us 300 over 10, so 30 hertz for 1 point there. Part B, if the mass weighs 3 kilograms, what must the spring constant be? So we are going to use one of our equations for a mass on a spring here. I'm using this one because, well, I just got frequency, and it leaves the spring constant k in the numerator, so I don't have to worry too much about reorganizing this equation as much as I would have otherwise. Just one or two less steps here. So first, let's rearrange this formula. I'm going to multiply everything by 2 pi, so I get 2 pi times the frequency equals the square root of k over m. Okay, I'm going to square everything, so I get 4 pi squared f squared equals k over m. Moving over here, multiplying everything by m, I get 4 pi squared f squared m equals k. Flipping it around and plugging in numbers, I get 4 pi squared. My frequency is 30 squared, and the mass, we're told, is 3. This gave me an answer of 106,592 newtons per meter. Very large spring constant here. Very, very large. Okay. C. A physics student sets up an oscillating pendulum of length 0.2 meters. The student wants the pendulum to have the same period of oscillation as the mass on a spring from above. So we're going to have the same period as this one, so we'll have to go ahead and calculate that. We know that the period is 1 over the frequency, which is equal to 1 over 30 hertz. So we know we're going to have a period of 1 over 30, or 0.03 repeated seconds. So we know that will be our period, so we'll end up using that. The actual question is, though, will this pendulum length work if this pendulum is on the surface of Earth? 4 points. Okay. And then there's a hint there. Is the length of the pendulum too long, too short, or just right? So, the way I looked at this, we can use one of our equations for the period of a pendulum. So I'm going to use this one here. And we just got our period there. And we can go ahead and plug in all the other numbers on the right. We have a length of 0.2 over 9.8, and we have 2 pi. So we can go ahead and calculate. Writing these both in decimal form, I get about, and I'll go ahead and round here, but I get about 0.9 on the right. So therefore, these are not equal, and therefore, it will not work. So you don't actually have to state if the pendulum is too short or too long, but if you go ahead and do some of the math on your own, you will find that the pendulum is too long. It needs to be about 1,000 times shorter. So if you go ahead and do the math for that, you should get something that says it's about 1,000 times shorter. So good luck if you try it. These were the answers for questions 2 and 3. Moving on. Question 4. A string of length 0.5 meters is fixed at both ends. Waves on the string travel with a speed of 100 kilometers per hour. All right. Write the third wavelength that allows for resonance. So resonance tells me that I'm going to have to use my resonance formula here. And this vertical-ish looking line is just my crappy lowercase cursive L that I've drawn. Won't have to see that for too much longer, though. So rearranging for lambda 3, because we are looking at the third order wavelength here. Rearranging, I'm going to multiply everything by 2, so I get 2L in the numerator. is an even worse L. Whatever, we'll leave with that. So 2L in the numerator, and we end up dividing by n, which we have replaced n with 3. Moving over here and plugging in for L now. We have 2 times 0.5 over 3. That gives us a wavelength of 1 over 3 meters, or just 0.3 repeated. So that is the wavelength. And part B, find the corresponding frequency for your answer in part A. We are given the speed of 100 kilometers per hour, so we are going to use the wave equation here. And first we need to convert from 100 kilometers an hour to meters per second. So for the velocity, that is 100 kilometers per hour. Divide that by 3.6, and you will get about 27 meters per second. So plugging in here, I did mine all in one big calculation, so I don't have that exact decimal memorized either, but it's about 27. And taking the wavelength from part A as well, so we have 100 divided by 3.6 on the top in brackets, and on the bottom we have just 1 divided by 3 in brackets, and all of that together you should get 83.3 repeated. Hertz is our unit there as well. Almost forgot. So that was everything for question 4. Question 5. A wave is described by the following function. Y of x and t is equal to 12 times the cosine of 2 pi times x over 5 minus t over 6.4. State the amplitude, wavelength, period, frequency, and wave speed. So amplitude, wavelength, period, frequency, wave speed. Okay, so amplitude, that is 12, just the number out front there. If you compare this with the formula on the formula sheet, you will see that x is divided by the wavelength, so the wavelength is just 5. You will also see that period is what t is being divided by. So you have lowercase t divided by uppercase t on our formula sheet. So the period is just 6.4. So 3 of these we're able to just pull straight from the equation without doing any calculation. So for this, we know that frequency is 1 over the period, which is 1 over 6.4, which is 0.15625, and keeping all of these decimal places will be necessary. So 0.15625, and lastly, finding the wave speed here, we get frequency times wavelength, which is that decimal we just found, multiplied by our wavelength, which is 5. So this gives us 0.78125. 78125. There we go. And so that was everything for part A here. B, rewrite this wave function using sine. So let's go ahead and do it. Specifically, we wanted it written in this form here. And we have phi, a phase shift in radians that we need to account for as well. So writing everything out, my A for amplitude is still 12. Here we have sine 2 pi x over a lambda, my wavelength, which is 5, minus f, which is my frequency, so 0.15625 times t, plus my phase shift, which is pi over 2. That is my conversion. It's a 90-degree offset, or a pi by 2 offset in radians between sine and cosine. In this case, I'm going to be adding pi over 2 to go from sine to cosine. So this was the answer here. 1 point for plugging in everything from part A correctly, and 1 point for getting the phase shift correct. Part C, verify your sine function by substituting in x equals 15 and t equals 8 to your sine equation and the given cosine equation. You must do this in radians. Okay, so let's do the cosine first. The given I'm just realizing now I wrote x and t. I will go back and fix that right now. X is now 15, t is now 8. Now, plugging this all into your calculator, you should just get 0. But what you should also just get is about 3.5 pi in here. I believe that is what the number was. Yeah, it should be 3.5 pi in there. And so any half integer, any 0.5 value, any half value of pi here for the cosine function is going to give us 0. So without even setting your calculator into radians, you can solve this and get the correct answer. So now for our sine, this is just going to be the exact same, but with as what we have written as our answer in part B. Now this is why I said we need to keep track of the extra decimal points. If you didn't use this full decimal here, you probably did not get the correct answer of 0. You needed all the decimal places to get the correct answer here. Plugging in, this should give you about 12 times the sine of 4 pi, and any whole number integer value of pi, integer multiple of pi, in the sine function gives you a value of 0. So therefore, they are equivalent. They both equal 0 when plugged in. So that was everything for questions 4 and 5. Question 6. A double slit experiment uses light of wavelength 520 nanometers. The slits are separated by 0.055 millimeters, and the interference pattern observed on a screen, and the interference pattern is observed on a screen 2.8 meters away. A particular bright fringe is found to be 3.4 centimeters from the central maximum. Determine the order m of this bright fringe. So this is going to be a double slit interference question. That's my formula. I will rearrange that for m because we are looking for m. Multiply everything by d, divide everything by lambda L, and plugging everything in. X, I have 3.4 centimeters, so that's times 10 to the negative 2. D, I have 0.055 millimeters, so that's times 10 to the negative 3. Here I have 520 nanometers, so times 10 to the negative 9. and 2.8. Already in meters, no need to convert anything there. Plugging all of that in, we should get about 1.28, or m equals 1. I accepted either. So that was question 6. Question 7. A parallel light beam containing two wavelengths of 400 nanometer and 800 nanometer light enters the silicate flint glass of an equilateral prism, for which the index of refraction of the glass is 1.49 and 1.46 respectively. So we'll go ahead and color code this for now. At what angle does each beam leave the prism? So we are given here a 30-degree angle of incidence. So let's go ahead and calculate. 400 nanometers there, 800 nanometers here. Okay, so I'm going to have to start by doing a sine law, or not sine law. Keep calling this sine law, even in class. It's Snell's law. Just happens to use sine. Rearranging this for theta 2 equals sine, or inverse sine, arc sine, whatever you want to call it, times the sine of 30 over the 1.49 value. And here we are assuming that outside of the prism there is air, so that prism is surrounded by air, so n1 is equal to 1, so we basically just ignore it here. This leaves us with a theta 2 equal to 19.6072316.4. Okay, great. Now we need to figure out what the angle of incidence is on the opposite side of the prism after the light has traveled through the full prism. We're going to use our little geometry formula here and rearrange this for phi 1, which is just going to be a minus, where a is 60 degrees minus the 19 degree value we just calculated. And that makes phi 1 equal to just a little bit over 40, specifically 40.39276836 degrees. I guess all of those should be degrees. And lastly, a second sine law. This time I'm going to have n2 sine phi 1 equals n1 sine phi 2. Rearranging for phi 2, this would be the arc sine of 1.49 times the sine of 40.39276836. And that gives me a final answer here of 74.92 degrees. So that was the first half here. Second half. It is the exact same method. However, we just have a different index of refraction that will slightly change our numbers. Is 0.03 less, so our numbers will change accordingly, and we end up with a theta 2 of 20.0271724.8, and then we get a phi 1 of 39.97282752. Again, just using the exact same method as written in blue. And phi 2 again, just calculated the same way. 39.972825752. And we get a final value for phi 2 of 69.71 degrees. Okay, so that was everything for questions 6 and 7. Question 8. Monochromatic light of wavelength 550 nanometers falls on a slit. If the angle between the third two bright fringes on either side of the central maximum is 40 degrees, estimate the slit width. Okay, so this is a single slit diffraction. I know I will be using m lambda equals d sine theta. I know I will be using this, and I know I'm looking for slit width, so I know I'm going to have d equals m lambda over sine theta. So what are these values going to be? Let's look at that first. We know that this is the third bright fringe. We're looking at the third two bright fringes. So bright means we are going to be looking at the 1/2, the values over 2, and third means we're going to be looking at the third one in the series of possible m values. So this is going to be m equals 7 over 2, and that is what we will be using here. Basically, just pick that value off the formula sheet. And wavelength, don't need to touch that. That's already in nanometers. We're fine there. We'll just make sure to convert that to meters when we plug in. Theta. This is the maximum, our peak here. And we have been asked, or we've been told that this angle here is 40 degrees. We want exactly half that. So theta equals 40 over 2. So plugging in, we get 7 over 2 for m. We get 550 times 10 to the negative 9 for the wavelength, all over the sine of 20 degrees. And all of that together should give you about 5.628 times 10 to the negative 6 meters. And that is the answer I was looking for here. Number 9, a diffraction grating has 4,800 slits per centimeter and is illuminated normally with monochromatic light of wavelength 520 nanometers. What is the highest spectral order that can be observed? So this is our diffraction grating question. So I will pull that equation out right here. Sine theta equals m lambda over d. We are going to be looking for m. So rearranging, multiply everything by d, divide everything by lambda. I get d sine theta over lambda. All right, let's figure out what these values are. We are given lambda, and we are not given anything else. D is not just 4,800. D is equal to 1 over slits per meter. Okay, well, here we have 4,800 slits per centimeter. There are 100 centimeters in a meter, so I will have 100 times this value in a meter. And so D is going to be equal to 1 over 480000. So 480,000 is what this actually is, not 4,800. And we are also looking for the highest spectral order that can be observed. So we need to try to max out sine theta. The maximum value that the sine of theta can have is 1. So sine of theta will be equal to 1 So this ends up getting us 1 over 480,000 times 1, all over our wavelength of 520 times 10 to the negative 9. And this over here, just moving it over to the right, gives us an M value of like 4.006 something. M just equals 4. So that was our value here. And number 10, how thick minimum should the air layer be between two flat glass surfaces if the glass is to appear bright when 600 nanometer light is incident normally? What if the glass is to appear dark? Okay, so for bright and for dark, I'll do these calculations separately like this. Using our formulas, this is what we have here. Okay, so let's go ahead and plug in the minimum possible value for M here. Because we're given wavelength, we're asked for T. Let's go ahead and plug in the minimum possible value for M, see what we get. Minimum value here is 0. We have 600 nanometers. And I also divided everything by 2 at once here. That will give me 150 nanometers as my final answer. All right, let's try dark. If I plug in 0 for M, and 600 times 10 to the negative 9 over 2, I'm going to get a T of 0. That's not going to work. So, because that is just basically trivial solution, so instead we're going to plug in 1 for M, all over 2, and we get 300 nanometers. So that was our answer here for questions 8, 9, and 10. Moving on, just a couple more to go. Our Michelson interferometer is illuminated with a light of wavelength 600 nanometers. The movable mirror is displaced by 0.2 millimeters. How many bright fringes N are counted during this displacement? So we get N equals lambda, or N lambda equals 2D. Rearranging for N, we get 2D over lambda. Plugging in, that's 2 times 0.2 times 10 to the negative 3 over 600 times 10 to the negative 9 equals 667, or just 6.6, or 666.6 repeated. Number 12, 3 ideal polarizing sheets are arranged in parallel planes. The second sheet has its transmission axis oriented 30 degrees relative to the first sheet. The third sheet has its transmission axis oriented 75 degrees relative to the first sheet. Both of these are relative to the first, and unpolarized light is incident on the first polarizer. What percentage of the original light intensity emerges from the third polarizer? Okay, so first let's start by writing down the fact that half of the original unpolarized light will make it through the first filter. So 1/2 I0 will make it through the first filter, and that amount of light I will call I1. I2, the amount of light making it through the second filter, will be equal to the amount of light that goes into it multiplied by the cosine squared of the angle theta, or in this case 30 degrees, between the transmission axis and the axis of polarization. or in this case, just the angle between the first sheet and the second sheet. Subbing in for I1, that is 1/2 I0. Cosine squared of 30 is equal to 3/4. So this is 3/8 I0. That is what I2 is equal to. And now for the third polarizer, the amount of light that comes through the third polarizer is going to be equal to I2 times the cosine squared of the angle between the light coming from the second polarizer and the transmission axis of the third. So this theta here is actually going to be 75 minus 30. So there's a 45-degree difference between these two here. So you don't just take 75, you take 45. And plugging in, we get 3/8 I0 for I2. And the cosine squared of 45 is just 1/2. So I3 is equal to 3/16 I0. I'm going to go ahead and just write that as a decimal. So that is 0.1875 I0. And this decimal here represents my percentage. This is 18.75% transmitted. So this percentage of light is what is transmitted through the third polarizer at the end of this little optical system. Moving on to the final question of the assignment, Brewster's angle here, or the polarization angle. So unpolarized light traveling through glass is incident on a layer of water at an angle of 41.8 degrees. The index of refraction for glass and water are 3/2 and 4/3 respectively. Determine if the reflected light is fully or partially polarized. Okay, so start by writing out our polarization angle formula here. We're going to solve for theta p. So we take the arctangent of both sides. The second medium here is water, so I will put 4/3 on top and 3/2 on bottom for glass, because that's where the light is currently traveling through. It's going to hit water. So water is N2, glass is N1. And here I get about 41.6. By 41.6, yeah, and it rounds down to 6. Okay, 41.6 degrees. Therefore, it is partially polarized. This is because although 41.6 is very close to 41.8, they are not equal, so it will only be partially polarized. And that was everything for this test. If you have any questions, please email me or ask me in class. Thank you.